Friends, welcome to the 25th lecture in module 1. In the previous lectures on 3D analysis, we discussed about how to evaluate transformation matrix, rotation matrix, how to estimate the direction cosines and the psi angle, which are very important for analyzing beam elements or truss elements oriented in space at its arbitrary location with reference to the x, y, z axis. Let us apply this logic and extend our knowledge of 2-dimensional analysis into 3-dimensional frame structures in the same style. So, the primary objective is to extend the knowledge of 2-dimensional analysis to 3D analysis. So, we have to follow the same set of expressions and equations with a small modification, which will make us to understand very easily and much faster how to use those transformation in a simpler form to do analysis of 3-dimensional space frame structures. As usual, we will consider a fixed beam for our analysis as a beam element. And we all agree that there are two nodes for the ith member, namely j node and k node. Each node now will have 3 translations and 3 rotations degrees of freedom, making it 6 in each node. So, the beam element now will have 12 degrees of freedom, which makes the stiffness matrix a size 12 by 12. That is the first difference. In 2D analysis, we had seen that the member matrices can be of size 4 by 4 if you neglect axial deformation, or 6 by 6 if you include axial deformation for non-orthogonal members. In this case, it will be 12 by 12. Let us take a simple member arbitrarily oriented. Arbitrarily oriented with 2 nodes, 2 nodes. Let us mark the nodes as j and k. There is an ith member, that is the member designation. So, as usual, this figure is going to mark the local axis system, and this figure is going to represent the reference axis system. Okay. So, if this is the member orientation, we all know that this is going to be my xm, 90 degree anticlockwise to that is our ym, and this is z. This of course is true in both the cases. Let us mark the axis for marking the degrees of freedom in both joints. Okay. Now, let us mark the translations at the jth end. First, along x axis. So, let us first mark the axis. Okay. So, let us mark the displacement along x. I call this as delta t, that is the suffix we are using, and along y, which is delta r, and along z which is delta V. Okay. Then rotation about this. So, put your thumb towards delta t direction, remaining 4 fingers will point the rotation. So, let us mark it this way as theta L, or one can mark with double arrows also. Okay. L, then theta n, and of course, theta p. Now, let us come to the kth end, displacement along x delta h, along y delta s, and along z delta w. This is what we have used earlier in our derivation also. Okay. The rotation about h, that is x axis. So, we call this as theta m, and this as theta o, and this as theta q. This is what we have used in the earlier lecture also. Now, this is marked as per the local axis system. I want to mark them for global axis in the similar manner. Let me mark the axis first. Let us say this is my x axis, this is my y axis, this is my z axis, the reference axis system. Let us mark the corresponding displacements. So, this is going to be along x, which is going to be delta t, but with a bar indicating it is reference axis system, delta t, then delta r, then delta v, then rotations theta L bar, theta n bar, and theta p bar. Similarly, here delta h bar, delta s bar, and delta w bar, theta m bar, theta o bar, and theta q bar. So, we have now two sets of degrees of freedom, one expressed in local axis system, other expressed in global axis or reference axis system. Okay. Having said this, it is assumed now that orientation of the local axis system with respect to the reference axis system can be described in terms of the direction cosines, Cx, Cy, and Cz, and the so called psi angle. We also know Cx, Cy, and Cz are given by xk minus xj by Li, yk minus yj by Li, zk minus zj by Li, where Li is root of sum of squares of these Now, the set of translations at jth end measured in local access system can be connected to the reference access system as below. Let us say the displacements are delta t, delta r and delta v for the ith member at the jth node, is it not? So, this can be now connected to C11, C12, C13, C21, 22, 23, 31, 32 and 33 of that of delta bar t, delta bar r and delta bar v of the ith member. So, now one can see very clearly here this equation connects the translation at jth end, is it not? Call this equation number 1. Similarly, one can also write down for rotations, that is theta L, theta n, theta p is now again connected to the global rotations, whereas these are connected, which are nothing but rotations at jth end, equation 2. I can also do the same thing for the kth end. Let us do that quickly. Delta h, delta s, delta w is connected to that of the global displacements by this matrix, whereas these are connecting translations at kth end, equation 3. Similarly, I can also connect rotations at the kth end, which will be theta m, theta o, theta q, theta m bar, theta o bar, theta q bar by a matrix C 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3, equation 4. So, now I can combine all these 4 equations and write in one form. It will be all the 12 displacements, okay, which will be delta t, delta r, delta v, that is translation at jth node, theta L, theta n, theta p, rotations at jth node, h, s, w, translation at kth node, rotations at kth node can be now connected by a transformation matrix to the global, which can be delta t bar, delta r bar, delta v bar, theta L bar, theta n bar, theta p bar, delta h bar, s bar, w bar, theta m bar, theta o bar, theta q bar. Okay. Now, each one is a 3 by 3 matrix, you have just now saw that. Okay. Let us divide this also into 3 by 3. Okay. So, this is 12 by 1, this is also 12 by 1. So, this has got to be 12 by 12, is it not? So, this is C 1 1, C 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3, and remaining all are zeros. Similarly, 1 1, 1 2, 1 3, 2 2, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. This is the second set which we just now derived. I am just combining all of them. Okay. The third one 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3, remaining all are again 0. The fourth one is the last one 1 1, 1 2, 1 3, 2 1, 2 2, 2 3, 3 1, 3 2, 3 3. You can combine them. Okay. So, now I can write a single expression saying the displacement of the ith member of the space frame is connected to the displacement of the member of the space frame in reference axis system by a transformation matrix which is derived for the space frame for ith member. I call this equation number 5, where T I in simple terms can be expressed as C I 0 0 0 0 C I 0 0 0 0 C I 0 and remaining all are zeros C I. So, only the diagonal members, okay, only the diagonal are C I, which are all exactly 3 by 3. So, that makes 12 by 12. Okay, that is the transformation matrix in 3D space. Okay. Having understood this, the transformation matrix has special properties as applied to conventional 2D analysis. The transformation matrix in space of the ith member transpose will be exactly transformation matrix in space of the ith member with inverse, and hence the elements of the transformation matrix whose transpose is also applicable to the same algorithm. Therefore, delta bar I can now be simply said as T transpose of delta I, okay, where the C matrix is called the rotation matrix whose elements are the direction cosines, okay. So, C y can be used for y z x transformation and C z can be used for z y x transformation, which contains the direction cosine and the psi angle, correct. So, friends, one can also say the equations which are done for 2D analysis are also valid for 3D analysis, like the member end reactions will be given by T I of global reactions. Okay. If you want to find the global stiffness matrix, I can say it is T transpose K local of T of space. Okay. This is valid. Similarly, if you want to find K unrestrained into delta U unrestrained will give me the joint load unrestrained. So, then end moment of the ith will be k of ith transformation matrix of delta bar plus FEM of the ith member. All these relationships are valid, which have been actually derived and applied for a 2D analysis. Let us look at the summary now, friends. We are extending the process of understanding 2D analysis to 3D analysis. We derive the transformation matrix which connects xm, ym, zm responses to x, y, z system, which can be established for any member which is arbitrarily oriented. The transformation matrix contains direction cosines and properties of psi angle which need to be estimated for each member in this space frame. We will take up an example in the next lecture and try to solve this problem and apply the concept using computer program. Thank you very much.